All right, so if you think about last semester in chapter 13, it's about property of colloid and solutions, right? So now I want you to discuss with your table mates or your friends what generally will happen when you add salt to water. What will happen to the boiling point and melting point? Do not use your textbook. Discuss with them and then state why boiling point and the melting point would change when you add salt to solution, when something is dissolved in a solution. So in solution, there are two cases, right? One is ionic solute, and the other one is non-ionic solute, such as glucose. So generally, with added solute, your boiling point increase, and then your melting point decrease. And in 13.6, I want you to make a note, write it down, go back to that chapter. 13.6, there's something called Van Hoff factor. You do not need to read it now, but that's something you can revisit. And we'll come back to this concept because in the last period, I talk about activity. I talk about the coefficient may not always be the same. So some of you asked me whether I can talk about the activity coefficient. What is that all about? So in fact, last semester, you guys were exposed to this concept, okay? It's just one small paragraph in your textbook, but I find it difficult to explain this whole concept without thermodynamics, but I'll try my best, though we'll come back to this problem later on. So I want you guys to remember, when you dissolve salt, generally the boiling point will go up because as the liquid wants to become the gas phase, it has to escape from the intermolecular forces, right? So the added solute would potentially interact with your water molecule or your solvent molecule. And your melting point will decrease, the melting point depression. That is because in order for your substance to form a well-ordered structure, it had to deal with the dissolved salt solute. It had to find a way to put it, okay? So for example, you put Coke in the freezer. What will happen when you let it warm up to room temperature? It becomes flat, right? Because under the standard condition, it's really hard to have the gas, the dissolved CO2 to crystallize with your water. Okay, that only happens at very high pressure when things are different. Okay, so we'll revisit this concept and then you will see why I'm bringing it up. So last lecture, we talked about the Henderson-Hasselbalch equation, so which relates your pKa to your pH, and we're talking about buffer system. A buffer solution is a solution that has some dissolved ionic species, and that can resist the pH change when you add a strong acid or strong base. So generally, when you do a titration of strong acid and strong base, you generally will get a curve like this, okay? So this is ml of NaOH added. And how fast this curve increase is really depend on the initial concentration of HCl that you're adding and the initial concentration of sodium hydroxide that you adding. And more importantly, you have to account for the volume change, okay? What is pH? How would you define pH? It's the negative log of what? Hydronium ion concentration, right? So what happened when you, think about it, what happened when you react acid and base? You generate a salt, right? I mean, these are ions, dissolved ions, and you generate water. And when we are talking about these equations, you have so many water molecules. The molar concentration is about 50.5 molar, right? So that's so concentrated, so you do not care in your calculation because you only focus on the change. So if you think about it, when this is the acid-base reaction you've seen many times, you're generating water, right? And then a neutral ion, sodium and the chloride, but your volume changed, so your concentration of acid will change. And this is what making the titration curve look like this. Okay, and then you will have an equivalence point. For these type of reaction, your equivalence point is pH equal to 7. And that is because water, the Ka and Kb, they're equal to each other. So if we look at a buffer system, and we're talking about a single buffer, you generally will see a curve like this. But so this is the case where a strong base is added to a weak acid. You will get the buffer region, and then once you consume all of your weak acid, remember what is a weak acid? That means it does not fully dissociate. So when you're adding strong base, this spontaneously dissociate into sodium and hydroxide, and then the hydroxide will react with the H or form a water molecule with your weak acid until to a point that all the H or proton on the weak acid are consumed. Okay, then you enter a similar regime of what you observe over there for strong acid. You get a sharp increase. And this point will be your pKa. Okay, so you've probably done titration experiment in your general chemistry lab. Have you guys done titration yet? Where you are adding the strong base slowly or strong acid slowly and observe the color change. Have you guys done the experiment like that before? And then this is the basic technique that chemists back in the day have to learn how to titrate stuff, learn how to make a solution with a certain pH. But for nowadays, I think you just need to generally have a concept of understanding what will happen when you mix a strong base with a weak acid. And vice versa. That means when you mix a strong acid with a weak base, you will also get a buffering system. But what you observe will be an opposite plot than this. All right, so let's talk about the theory of pH. So this is the general equation of Henderson-Hasselbalch equation. You do not need to memorize this. This will be given on a test, but you should understand what this means. So like I said last time, if the concentration of your conjugate base and your weak acid are the same, you will get a ratio of 1, right? A log of 1 is 0. So that means when pH equal to pKa, in this scenario, what's happening to the weak acid is that their conjugate base concentration is the same as its own concentration, okay? And that gives you the origin of buffer capacity. And from, I think, 2 lectures ago, I mentioned buffer capacity is how much base or acid a solution, a buffer solution can handle without significant change in its pH. So the more concentrated your buffer, generally it can balance more added base or added acid. And then your initial pH of your solution is determined by, well, the Ka is the intrinsic property of your weak acid and weak base. Okay, this is the equilibrium constant. Unless you change temperature, usually at room temperature, Ka is constant, okay? But then you can adjust the initial pH by changing the ratio of your conjugate base or conjugate acid by adding the salt form of it. And how would you get a salt from acetic acid? You're simply adding a strong base. And then generally, you will get a form like this. So in a lot of, this gives you an acidic flavor, like vinegar. So in a lot of food additive, you will see sodium acetate being added. So imagine you have a solution of acetic acid. Its Ka is on the order of 10 to the negative 5. So to put that into perspective, let's think about a 0.1 molar of acetic acid. If we do the math, everybody know how to do this math to figure out your pH from your Ka? Okay, just simple math, okay? That corresponds to about 1.3% of this acetic acid will dissociate. Okay, so 1 in 100 will dissociate into acetate and then the hydronium ion. But when you dissolve sodium acetate to the solution, this thing spontaneously dissociate, okay, into acetate and sodium ion. Okay, so this acetate may pick up another proton, but basically it generates itself, okay? But the ratio of this, what this is telling you is the position where you are on this curve. And this may seem flat, but if you look out a little bit, this is not a flat curve. Okay, you will get a part that is flat, but then it will start going upward or downward. Okay, and when we adding this, it will change the pH. And this, we know a weak acid conjugate base is strong, right? It wants to become its old form. So if you're taking away the hydronium or proton from water, it's basic, right? So initially, a 0.1 molar acetic acid will have a pH about 2.7. But if you're adding a little bit of base, this is called titration. Once it reaches the equilibrium, for example, if you're adding some sodium acetate, it can, once it at the pKa value, you will generally get a solution that has a pH of 4.7, which is the buffering region of it. And then to put this into perspective, the ratio of these two, it generally, for it to be relevant, okay, when we're looking at pH, we're looking at it in a loss scale. So a factor of 10 is what matters. When you increase pH by 1, that means the total concentration of hydronium ion increase by 10. So generally for a buffer solution, when you want to prepare a buffer solution, you first have to look up pKa. And then generally the capacity is about 1. Okay, so within plus minus 1, it can retain the pH at the desired value. Once you go above or below, when you have too much base, you will get a titration curve like this. So let's try, in your book, if you flip to the back of the book, there is a Ka table. I would say it's Appendix C, A through the 8. So from this table, you can see a lot of Ka over a lot of organic molecule. And I want to point your attention to if you look at these simple acids, such as formic acid, it's a little stronger than acetic acid. And then I also want you to look at the glycolic acid. So these are very common acid that is seen in nature. Okay, so if we want to make a solution with the target pH, okay, so generally buffer solutions are used in biological systems. So for example, if you want to culture cells, you will use a buffer solution. And then generally CO2 is also utilized as a ingredient that control pH because CO2 can dissolve in water and form carbonic acid. Okay, so that explains why the water, when it's left out in air for a while, the pH change. Okay, that's why when you go into the wild, when you collect water sample, they're not 7. It really depends on the mineral or ion that is dissolved in it. Okay, so let's talk about some organic acid. So when you work out, when you run, your muscle feels sore. It's because your muscle needs energy. When it breaks down a common energy source that is stored in your body, you form lactic acid. And the ones you take in biochem, you will see a lot of organic acid is being produced by our body. So the lactic acid, it has a pKa of 3.86, but then similarly, the glycolic acid, it has a pKa of 3.83. So formic acid is produced by ants as a self-defense mechanism, okay? So it's a weak, even though it's a weak acid, but it will still hurt, right? Because it's a concentrated form for the ant to excrete out. And once it wanted to, because it still want to dissociate to some extent, right? So your local pH will likely to be very high. Again, pH is dependent on the concentration. Okay, so remember I said the target pH we want is 3.9. Okay, so these pKa will have the highest buffering capacity. Okay, but in the book we did not really specify why we need a solution like that. But if we consider biochemical process will rely on these two important intermediate, right? So we do not want to interfere our biological process, right? Because if your sample also contain ions of these, you're messing with your simple calculation. So this is just to show, okay, with a minor change in their chemical structure, your pKa would change. And generally, if you still recall, how do we define the strengths of various type of acid? It has to do with whether it can stabilize the corresponding ion that is formed, right? So generally, if you have a strong electron withdrawing ability, this is also applied to organic acid. If you have a strong electron withdrawing capability, you generally become more acidic. All right, so from the, if our pH is listed there, we can calculate how much base we can add in to make our buffer solution based on formic acid. Okay, so we simply put pH here, and the pKa is 3.74, and plus, and then you have this log term here, right? And that will give you what ratio of these two needs to be to get to this pH, right? So we can solve for this equation. We simply minus 3.74 from both sides, and in the end, you can get this equation. And then if we try to remove the log, 0.16 come from 3.9 minus 3.74, you get a ratio of these two. There are several ways that you can make your buffer. One way is you can start with pure HA, pure weak acid, and add in base until you get to the buffer region. Alternatively, is you can look at this equation and adding the sodium or potassium adduct with the conjugate base of your weak acid. Then if we solve for this, we can get how much conjugate base you will need to add into the system to achieve this pH of 3.9. This is a very important calculation that you guys need to know how to do. And then just to put this into perspective, a common buffer that is used, so last time I mentioned PBS, so it's the phosphate-based buffer saline solution. Okay, so generally this solution will have some salt, and the reason why the sodium and potassium are both there is because in your body, these are the two most common ions that are present. So you can see this is a buffer that typically have the working range of 7.4, so very similar to our physiological condition. And then the phosphate, as I mentioned before, the P04 is actually a weak base, right? Because it exists in multiple equilibrium. And that's why these salts are generally added. But in reality, I think most lab will buy their buffer because to be consistent, to avoid human error, you are likely to buy a concentrate or a package of your buffer powder, these salt, and then you just dissolve them. And more importantly, is after you prepare your solution, this equation is ideal situation. Okay, in reality, even you do your math perfectly, you weigh out your compound accurately, you will not get the pH that you desire. Okay, so dissolved CO2 being one possibility. And also there are like some trace ion present, so it change your equilibrium. So generally, in the end, after you make your solution, we were still adding strong acid or strong base to adjust the ratio, the actual ratio of these two, so that you can get to the starting pH that you have. Okay. Other kind of buffers. Okay. So just to show you some structure. So this is based on inorganic. the phosphate, the multiple equilibrium of phosphoric acid, right? So a lot of organic compounds are used in biological experiment. For example, tris, I know it's weird looking compound. The hydroxyl group make it capable of hydrogen bonding, so make it water soluble. And this part, it's a weak base, okay? So it generally have a weak pKa of 8.7. And remember, I had a buffer capacity, right? That means you can generally make a system that can buffer between these two pH, okay? And the other kind of buffer, it's a citrate buffer. So where you might guess citrate can come from citrus fruit, right? From like orange, lemon, they have a lot of citrate, and it's hydrogen form of it, the acid form of it. So the structure, it's a multiple carboxylic acid, okay? And sometimes you may guess, oh, these are carboxylic acid, their equilibrium constant must be the same. However, this is not the case for a lot of organic acid, okay? After the first proton is lost, the pKa of these things are different, okay? Because it's constantly in the equilibrium. Just so that you know the Ka value, the pKa at 3 pKa, okay? These 3 protons, the equilibrium constant varied by a lot, okay? So that makes this citrate a very useful buffer system because it has multiple Ka values that can keep you in a range of 2 to 4, and then it will have a rapid increase. You go to the next equilibrium between 5 to 7, and or this one is buffered between 3 to 5. So it really depends on where you are. So likely for titration of this is going to be a very challenging one to actually observe a well-defined curve. Let's work on more example before we go back to our strong acid titration curve. So we have a sodium bicarbonate, okay? So this can also make a buffer that is more on the basic side. We know if we lose the hydrogen, you will form sodium carbonate, right? So when we have a target pH, we know, I'll give you the Ka of this. And we note that this is very small. So that means it actually prefer to be in this form than the carbonate form. Okay, so by doing the similar thing over here, that makes sense, okay? This is exactly what you see here, except this starting acid had the charge. So don't get distracted by the sign on these ions, okay? And we know let's say our target pH is 10. And then from a Ka, we can calculate pKa, right? And then we can figure out the ratio between these two. Okay, so from this, because we know this dissociate completely, so we can calculate the amount of HCO3 that is present initially. Then we can do the simple math to figure it out how much sodium carbonate we would need to add for us to bypass the pKa of your starting material and then to get to the pH that you needed. So if you do the math, if you correctly, you will get to 15 grams. So this is one of the example that is in your book. So if you have questions, you can look at example problem 19.3. Let's go back to the simple calculation, strong acid and strong base, because we already know where this comes from, okay? And then for titration, back in the day, people will use some organic compound that change color, okay? Nowadays, you can have automated titrator that will just titrate your solution for you and tell you exactly where these transition points occur. It's all automated, but unfortunately, in the laboratory, you will still need to practice these skills and understand how to do these math. All right, so if we go back to this scenario, so we have example 1. If we have 40 milliliter of 0.1 molar HCl and 20 milliliter of 0.1 molar NaOH. So we know these two will react immediately, right? Where do you think we might be on this curve? we will likely, because the amount of base did not exceed the acid, right? So you were in between these region, okay, between A and B. Okay, so, but again, like I said, I want you to remember, this is a concentration term. Let's say a 0.1 molar of HCl, if I dilute it by a factor of 10, it becomes 0.01 molar. What happened to my pH? It will change, right? Okay, so similar to this case, okay, we know the amount of hydronium ion that was present initially, and then in the end it decreases because it reacts. But then, because we have these additional volume, we have to account for that. So we will, if we want to know the pH, so I do the math very quickly. I know I will have 20 ml left. So because we're talking about molarity, so it's mole per liter, and then it's 0.1, so 10 to the negative 4, and then this term will become 0.002. Your final volume is 40 ml and 60 ml. That gives you 60 ml, and that will be in liter. And that will give you the concentration of your acid that is present. So if you take the pH, so this is calculating for the hydronium. So your pH will be 1.48. And initially, you are at pH 1. Okay? So this is why I said it will be between A and B, likely to be in this region. So when you're thinking about a problem like this, you should have a mental image of where you are at titration curve. Okay, so let's look at the second example. If we're mixing 50 ml, now I want you to actually work on this problem. Okay, write it down. Okay, so I'll give you 5 minutes to figure out the amount of OH minus that you have. So we know this is strong acid. We know we can figure it out how much base that we have, right? And exceed amount of acid that is present. Okay, so still we know it's exceed by 10 ml. Okay, right? The difference is 10 ml times 0.1, and don't forget the volume change. So then you will get this, right? And then this is your OH. So when you do the POH, I mean, this should be negative log, okay? Because I have concentration here, you can get a value, right? So this will be 1.95. And then from the previous chapter, we know kW is 414, right? It's the scale that we set for such system. Then your pH would be 14 minus 1.95. And I want you guys to remember, so this will be about 12.05, okay? So I want you to remember this equation, Kw equal to Ka and Kb times Ka and Kb. And then and we did not go in depth regard to what Kb really is, but Kb is talking about the base that is formed, right? So the product will be hydroxide. Okay, so if we go back to the for example, in this case, if you take a proton away from the water, you're generating hydroxide. So if you're setting up your equation, you have your hydroxide on top as your product. In the end, that will be giving you value that is related to Kb. So mathematically, you can use your Excel sheet if you're interested, okay? You can use your Excel sheet, you can plug in numbers, okay? If you program your sheet, you should be able to regenerate the calibration curve, okay? Very simple calculation, okay? But most importantly, you have to account for the volume change. Okay, so let's say we have a very, very concentrated acid or very, very concentrated base. The amount that you're adding is so small that does not affect the overall volume. Then in that case, you can forget about it, okay? Then you can just do your math. But it's really depending on the magnitude of each of your values. So everybody understand the physical meaning of these curve? then we will start incorporating this equation in understanding a buffer system. Okay, so again, we're looking at a weak acid system. So you can look at your page 855. So again, we'll look at that problem similarly. So we'll compare two scenarios similar to that. First, we will have equal amount of your weak acid and base. Okay, so when you hear about weak acid and a strong base mixed together, equal amount, you should instantaneously think of or expect you will get a basic solution. So if you do not remember this, go back to previous chapter talking about acid and base. Or you can think about the KSP practice that we did. What is a weak acid? Okay, what does a weak acid do? When we think about a weak acid doesn't dissociate so much, it will take protons away from the system so that it reaches to equilibrium. Let's look at this. When they're equal amount, the base will abstract all the protons away immediately. So we can expect, so it will be the 19.4. Okay, that's what I mean to talk about. So if you look at page 858, okay, so if you put in the equal amount, okay, it consumes all the weak acid, right? So you form a conjugate base. So if you do the math, you can get the conjugate base, which is the propanoate. You'll get this anion, okay? So we know the concentration of this anion, okay? And then we know when you have a conjugate base react with water, you can set up the next equation. So the HPR is a propanoate with acid, the propanoic acid. So it's similar to the CHCOOH that you've seen previously. It's just a different acid, and OH minus. You know the concentration, then from this equation, you can easily figure it out the Kb, right? So remember Kw equal to Ka times Kb. Okay, so we know the Ka, so we can figure it out how much hydroxide ion could present in the system. So when we write out this, okay, again, the water is a liquid term, so it goes away. And then we can, the amount of this equal to each other, so we can set this to be x and simply solve for the x. And you will end up getting the OH minus. So similar to that problem over there, you can do it two-way. You can either using Kw to get how many hydronium ion that you could have, or you can go through the pKa calculation to do everything in log scale. And then so when we have equal amount mixed together, you're likely to be at the equivalence point, your pH 8.8. So this is where this comes from. But when you have excess hydroxide in such system, let's say we have a lot of hydroxide, 50 mil, so you are over this buffer regime, okay? So you're likely end up somewhere over here. So if we do the math, okay, so if you look at the part D, so it simply states that the hydroxide that added, part of that hydroxide is being used in reacting with the proton, generating water, but you have some residual amount. And more importantly, you are ending up with a lot of these anion, okay, your conjugate base. What to do with this? Because the amount of hydronium, the hydroxide ion dominate in this case, we can simply figure it out from using the Kw equal to Ka/Kb, or the hydronium ion concentration times the hydroxide ion concentration. Using that equation, you can figure out the amount of hydronium ion that is present at that state. So you can tell, okay, this is simple check. The amount of hydronium is so small, so this is likely to be a basic solution. So when you go over this equivalence point, you will get to the basic regime, okay? And then, of course, if you add acid, you can come back here, but again, your volume won't be the same. So your capacity will decrease, Okay, it's still within pH 1 and 2, but you have to think about the molarity of your weak acid. All right, so the example that we talk about today, I mean, you can, when we are talking about a weak base with a strong acid, I know last week in the homework assignment, you guys work on a problem on quinine, right? So remember, I mean, it's a little different than the chloroquine stuff people are talking about that they can combat this COVID-19. But the quinine is a very interesting one, and you don't really need to know the organic chemistry of quinine to solve the problem. It's just a simple concept of comparing the relative term of Kb and then compare, by knowing the values and know the strengths of acid and base. Okay, so the bigger Kb that means it's more basic, more likely to generate hydroxide ion. All right, so because the homework haven't been graded yet, so next period we will hopefully I will be able to give back the homework, and then we'll talk about that quinine problem, because I think most of you get the calculation right, but accept that problem because you probably used the wrong value despite what we discussed in the problem. Okay, so quinine, the reason why I bring that up, quinine is, okay, when you see tertiary amine, that is generally a very common weak base being used. I have a structure of tris, that is a weak base. So generally, unless there's special substituent on the amine, they generally behave like a weak base in aqueous environment. And so depending on the amine structure, if you look at your appendix C, you may see some pattern, and we'll come back to this a little bit more when we discuss organic chemistry in this class. Okay, so if you look at the figure 19.8, you're looking at exactly reverse of this. You just have to think about you're going from a basic solution, going through a buffer regime. Again, despite it's a base, you can still use this equation, okay? This doesn't change. You just have to recognize what loses proton and what gains proton, and you can figure out the correct position of each things. And then, so after you pass the buffering regime, generally your acid will dominate the solution pH. Okay, I hope that all makes sense. So we'll move on to complex ion. Remember the definition for Lewis acid, Lewis base? That is where we look at the electron donor and the acceptor when we talk about acid and base. So 3 definitions of Bronsted acid and base. You have to know that. This will be on the exam. Lewis acid and base, we know Lewis base are generally like amines. They're a good Lewis base. Water can be a Lewis base and an acid, okay? But ammonia is generally a stronger Lewis base than water, okay? So when we dissolve metal ion, due to the d orbitals, we'll talk about that later lectures. Because of the d orbitals, it have all these empty orbitals to interact with electrons, okay? Interact with various type of ligands. So when you dissolve a metal ion in a solution, okay, let's think of a very soluble salt, okay, and it dissociates completely. The ideal picture is you have a metal ion here, and the water molecule could bind to it, and depending on their electron configuration, okay, and depending on the metal, they will adapt different geometry. So in the coordination chemistry and inorganic chemistry, you guys will learn more about it. Okay, so but let's consider a simple case when we have a metal ion, it dissolves in water. Okay, so generally they like electrons, so it actually go to a state where the valence shell are full. But that electron is not really actually being held onto by the metal ion. It's more of their sharing And then this bond is generally more labile than the covalent bond. All right, so the metal, some metal likes to complex with 6 water, some like to complex with 4. So it really depending on the identity of metal. And in this case, let's consider nickel. So when we expose this to ammonia, because ammonia, NH3, is a better Lewis base or stronger Lewis base than water, okay, we can displace these ions. So when we write out, there's something called Kf, formation constant. So this is very similar to KSP, and I didn't really talk about it because we haven't really talked too much about these ions. I mean, the only example is where in the previous chapter you see the cyanide reaction or thiocyanide reaction with iron. Okay, so if we look at this has to appear stepwise. So the water can be displaced one by one, and eventually it will become, and this nickel is still charged. The water or the ammonia is simply because their lone pair is present on these molecules and it donated to the d orbitals of these transition metal. So before it gets to here, like I said, the stepwise exchange of a ligand, and this is the dynamic process. So in the Kf, we can write the exchange reaction. So in this case, if we think about the last step, so that's product, so you should be able to recognize where this will come from. This is basically product over reactant, similar to what we've seen before, except we're only looking at the last step because that is the compound of interest. Okay, so when there is something with multiple equilibrium, in previous chapter, we can times all the constant together, because if there's an intermediate, the term will cancel out when you combine all the equations, and you can get these Kf value. All right, so let's do a simple calculation. So in the book, there is an example of exchange reaction between zinc hydrate and zinc ammonia. So I believe this is in sample problem 19.13. So if you look at this problem, I mean, the way these equations are set up is really simple. I'll have you guys walk through it with your partner and work on the sample problem 19.13a. If you guys haven't finished, that's okay. But I'll continue talking about the complex ion because there's really not much to say about it. So generally, given that metal can form complex ion, it's gonna be able to change your KSP, right? So because it can increase the solubility of ions through complexation. So it's not a naked ion, what you would expect, basically ion with a hydration shell. And then I want you to look at the page 882. Now you can see this is a different case of complex formation. So we will see the aluminum will complex with water up to a point. So look at page 882. You see the precipitation of this aluminum species in the middle image. So that means the hydroxide is slowly reacting. The hydroxide ion itself is actually interacting with your aluminum metal, right? And in the end, it has some sort of acid-base reaction happening, right? So you are getting this somewhat clear solution, right? So that indicates the solubility of your aluminum species goes up. And this is a very important phenomenon because in organic chemistry, later you will see we will use aluminum as a reducing agent, okay? And your byproduct has to be removed from your reaction, and it really rely on such complexation reaction. Now I want to point your attention. Okay, so last semester we talked about ideal gas law, and to me it actually makes sense there are connections between gas and liquid, and so chemistry is all about making connections. So the way I teach is I try to find the things that I find there are some connections. So if you do not see the connections, that's fine, but try to figure out a way to make your own connection between different concepts. Because we don't have the thermodynamic component in this class yet, that's why I find Lec08 principle very important. That's why last lecture we talked about Lec08 principle, and we'll get back to it a little bit. But let's look at the deviation of ideal gas law. And this will lead to the explanation of effective concentration and also the case of complex ion formation. So last semester we talked about ideal gas law, and I remember JJ, you came up to do a demonstration on intermolecular forces, right? So everybody remember that? So here the plot that you're looking at is the real gas behavior versus what is predicted by the ideal gas law. As you can see here, as the pressure increased from one standard atmosphere, you have a huge deviation from the ideal gas law. At a reasonable temperature, we see somewhat a smaller deviation, but at extreme condition, okay, so now I want you to think about the molecule motion. At higher temperature, they have more kinetic energy, so they move faster. At a higher pressure, there's less room between each molecule. Okay, so if you can relate that to solution, in gas phase, you have all these freedom, but in solution, the probability of running into another ion, right, or another solvent molecule increase exponentially. So it's somewhat similar to the extreme case where the pressure is higher because your gas doesn't behave like ideal gas law, PV equal to nRT. And then some of you may or may not remember Avogadro's law. So that is a constant saying at 0 degree and 1 atmosphere, the volume of all gases will be the same. It's about 22.4 liter per mole of gas. All right, so things deviate from our equations. Now think about the kinetic theory of gases. So when we are in extreme conditions, it deviates from our theory, so we have to put some sort of correction term. And why it deviates from the equation is because our assumption is not valid anymore, okay, because the condition changed. So how does this link back? So if we remember, like ammonia, carbon dioxide, they have intermolecular forces, okay, so that changed the behavior of molecule. It's not a truly random motion anymore. At some instant, they may form as a cluster. Now think about solutions. Okay, so this is a complex ion formation, thioisocyanate. You've probably seen it before, all right? So the solution on the left is a 1 millimole iron chloride solution, and then you have 1.5 millimole, so slightly excess of potassium thiocyanate solution, right? Upon adding 10 grams of potassium nitrate, you see the color of the beaker on the right become lighter. So usually, if you remember Beer's law, the more concentrated solution, the darker it is because the light is being absorbed by these molecules, right? So this suggests the addition of potassium nitrate change the equilibrium, okay? So this is a little bit different than common ion effect. So there's no common ion. But in fact, it's the ionic strength that change the behavior of these ions. So when the ions are dissolved, okay, when they're fully dissociated, okay, so it depending on the distance from your atom or molecules. At different distance, your charged species experience different amount of forces. So at high ionic strength, which means you have a lot of ions, so think about it in a term where you have a compressed gas, the chance of ion running into each other, interacting with each other, the probability increase dramatically. In an ideal solution, the thiocyanate is able to approach the iron, 3+, right? But when you have other ion present in the system, there are some weaker interaction, but when your concentration of your other ion, even though the affinity for the metal is not that big, it still have Coulombic interaction. So the positive negative charge, they interact with each other. So it decreases the probability of things reacting with each other or colliding with each other. So if you remember from the rate law that we're talking about, we have a rate constant K to account for what we didn't account for when we set up the rate law, when we set out the rate expression, right? Because every collision doesn't really result in an actual reaction. So you have these correction terms. Okay, so, and I know some of you may be confused by the concept of reaction order. So that is, in reality, reaction order, yeah, you can fit your experiment data to get the reaction order. But in reality, these exponents change. That is because effective concentration. So similar to this concept where you have additional interaction with your charge. So when you see a +3, it's not really a +3. So if you adapt that into the sense of solution, when I have a concentration of 1 molar, it's not really 1 molar, okay? Because of additional factors, the change in a deviation from your simple approximation. Therefore, similar to rate law, we will have a K in front of it to adjust for it. So for ionic strength or effective concentration, generally we have a correction factor in front of our actual concentration, right? So this can be any number. And this is the reason why the exponent up here is not the same as what you would expect from a simple bimolecular or termolecular reaction. Okay, that makes sense? You see the connections? I hope this answer what is an activity coefficient. So this is related to how can you better describe your reaction system or your system with an additional correction factor. So activity coefficient, these coefficient up here is what deviate from the physical concentration and the ideal value. So I hope that all makes sense. And finally, I would like to refresh on the Le Chatelier principles. So I see a lot of very good answer on your 1-minute paper. But basically you have to state that there's a two-part to the Le Chatelier principle. Okay, so the first part is at equilibrium, when you shift the equilibrium position, change has to happen so you can go back to the equilibrium position. And this is why I talk about this concept over and over, because this can explain why something precipitate, why the solubility increase, why the Kf is affected by added ions. Think about effective concentration. When you go to more advanced course, there will be more explanation on these terms. And then importantly, the catalysts do not shift K because catalysts only affect activation energy. Do not get confused because we have Van Hoff equation and we also have the Arrhenius equation. So Arrhenius with the A, it talks about EA, which is the activation energy. Van Hoff equation, okay, it talks about equilibrium constant, okay? And generally we do not care about the change in delta H, heat of reaction, because generally it's a constant, okay? But in extreme cases, it will be like ideal gas law, the thing will change, okay? And more importantly, recognize that the heat as a product of your chemical reaction. If your reaction system is endothermic, that is absorb heat, okay? So the heat is on the reagent side, okay? So if you add more heat, it's gonna give you more product. So and vice versa for the exothermic. It's the product, so you add in more heat, the reaction is gonna go backward, okay? Next period, we will hopefully talk about your homework and the experiment we did.